Hi Pa, good morning. So this is your third video lecture on Unit 1, and in this we'll see some very important terms and topics that will cover some losses defining your magnetic circuit. The two important losses in the magnetic circuit is hysteresis and the eddy current loss. So when a magnetic material is subjected to a cyclic magnetization, two kinds of power losses occur in it. So hysteresis loss and the eddy current loss, they together called as core loss. So first we'll see what is hysteresis loss. The magnetic circuit is subjected to the magnetic field reversal as it passes under successive poles. So see in this. So when you subjected to magnetic field, okay, when a magnetic circuit is subjected to the magnetic field reversal, see, because of this reversal, there will be some of the energy needed to reverse this magnetic field. Okay, that power is gone as loss. So that is your hysteresis loss in common. So see, it can sometimes some amount of power has to be spent to reverse the molecular magnets in the armature core continuously. It is considered as loss, the loss of power in the core due to this hysteresis effect. Okay, that is changing the direction of that magnetic field. Okay, that hysteresis effect is called as hysteresis loss. So the formula is given by Steinmetz, and the formula of hysteresis loss is given as pH, that is equal to kH into B max power of 1.6 into F into V watts. Okay, it is loss of power, so it is termed as in watts. So B max is equal to maximum flux density in the core, and F will be your frequency of the magnetic reversal. Okay, V is the volume of the armature in meter cube, and KH is equal to Steinmetz hysteresis coefficient. To reduce this loss, the magnetic core is made up of such material which have low value of this Steinmetz hysteresis coefficient, example silicon steel. Okay, I think you got the point. Next type of loss is our eddy current loss. In addition to the voltage induced in the conductor, so we know that according to EMF, an EMF is induced in the conductor. There is also a voltage induced in the magnetic core. Okay, see here. This magnetic core also, there is a voltage induced. These voltages produce a circulating current in the core. This is your core. Okay, there will be a production of circulating currents in the core. So because of that current, there will be a power loss. That loss is your eddy current loss. So that is given by P is equal to KE P max square F square T square into V in watts. So the P max is the maximum flux density in the core, F is the frequency of the magnetic reversal, and V is your volume of the armature in the meter cube, and T is the thickness, and K is the constant. So we have discussed the main two losses, that is hysteresis loss and eddy current loss. So next loss that will occur is the leakage flux. So what is this leakage flux? Is that the flux that is leaking in the air gap. Okay, so the stray flux which does not take part in the energy conversion. Okay, it will not convert into energy. This magnetical flux is not going to convert it into electrical form. Okay, so this stray flux which does not take part in the energy conversion is called the leakage flux. This flux can never be eliminated. We cannot eliminate this flux. The effect of leakage flux is incorporated in the machine model through the concept of leakage inductance. So see here. So some of this flux is the useful flux that is going to cut the another winding and will induce an EMF in the secondary and will convert it into electrical energy, okay, in the another form. Okay, but these are fluxes that is leaking out and which is not going to be useful. So that is your leakage flux. So next effect, that is adverse effect that will affect the magnetic field properties, that fringing. So what is this fringing is that the flux in a magnetic circuit bulges onwards while passing through the air gap. So bulges, that is your fringes. Okay, this result in non-uniform flux density in the air gap, enlargement of air gap area and reduction in the flux density. So when the air gap area increased, the flux density produced in the useful flux that is converted into useful form will be reduced. So that is the fringing effect. This phenomenon is called as fringing. The effect of fringing increases with the increase in the air gap length. So what is fringing? Fringe flux in the magnetic circuit bulges out while passing through a air gap. That will result in non-uniform flux density in the air gap, resulting in enlargement of air gap area and reduction in the flux density in the air gap. This phenomenon is called as fringing. It's a very important topic. It may be asked in 2 marks and in interview questions also. So next effect is your stacking factor. What is the stacking factor is, magnetic cores are made up of thin, lightly insulated lamination to reduce eddy current loss. So we know that eddy current is formed because of the induced voltages in the core, in the core. So if the core is being laminated, this eddy current loss can be reduced. Okay, as a result, the net cross-sectional area of the core occupied by the magnetic material is less than its cross-section. So we know that it has been stacked or it has been laminated. For if the single cross-sectional area, so because of that, the single cross-sectional area of this stack is going to be less than the overall cross-sectional area of that material. Hence, the ratio of that net cross-sectional area to the cross-sectional area, gross cross-sectional area, is called as stacking factor. I hope you understand. You know that. So this is your laminated core. It has been laminated. Okay, so this is having a one cross sectional, this is having another cross sectional, and this is having another cross sectional. So the ratio of the cross sectional area, to the gross cross sectional area is called as the stacking factor. Next, we'll see some properties of magnetic materials. All materials are classified according to their relative permeability. Okay, we know what is permeability. So they have been classified into 3, that is paramagnetic material, diamagnetic material, and ferromagnetic material, and ferrimagnetic material, that is classified into 4. So the materials are classified according to the relative permeability. So what is the paramagnetic material is that if the permeability, okay, that is air gap permeability of the material is greater than 1. If the permeability of the material is greater than 1, then that material is called as paramagnetic material. And if diamagnetic material is that if the permeability is slightly less than 1, okay, slightly less than 1, that is a diamagnetic material. So ferromagnetic material is when the permeability is much higher than that of free space. When the permeability is much higher than that of free space, then that kind of material is called as ferromagnetic and ferrimagnetic materials. Okay, so ferromagnetic materials are further subdivided into two, soft and hard. Okay, for example, we use such kind of materials in magnetic circuit. Either ferromagnetic, we'll use almost ferromagnetic materials for the magnetic property. So that is further divided into hard and soft. The hard materials examples are alnico, chromium steel, copper, nickel alloys and metal alloys. For soft nickel, it is iron and its alloy with nickel, cobalt, tungsten and aluminium. These are some of the properties of magnetic material, and some materials that is been used as a ferromagnetic material. Okay, almost these materials are used for the magnetic circuit. Okay, see this. Okay, we'll see in next class about the next unit. We have almost covered your first unit, the basics. Okay, thank you, ma.